My random variable x belongs to this interval 0 to 3, and it can occupy or it can be in any two intervals of the same size with equal probability. So x is uniform random variable. And whenever you have a uniform random variable, its PDF takes this form, 1 over b minus a for x between a to b, and it is 0 otherwise. You guys can see my screen, right?
Yeah.
Okay, all right. So in this case, b is equal to 3 and a is 0. So f of x in this case is 1 over 3 for x between 0 to 3, and it is equal to 0 otherwise. So that's the probability density function for this random variable. So that's the probability density function. And I need to find the probability that the random variable x has 3 after the decimal point. So if x were to be either between 0.3 to 0.4, or it were between, if it were to be between 1.3 to 1.4, or between 2.3 to 2.4, it's going to satisfy this condition that it is going to have a decimal number, uh, um, or it's going to have 3 after the decimal point. For example, 0.32 also belongs to this interval, 1.38 belongs to this interval, and so on, which satisfy this condition that there's a 3 after the decimal point. So I need to find the probability that x belongs to these intervals. And then I need to replace or with a plus and add those probabilities to get my final answer. So the probability that x has 3 after decimal point is given by an integration over this interval right here from 0.3 to 0.4 of 1 over 3 dx plus the integration over this interval 1.3 to 1.4 dx over 3 plus integration over the next interval, which is 2.3 to 2.4 dx over 3. And when I solve this integral, I get x over 3, and the limits are 0.3 to 0.4 plus x over 3, 1.3 to 1.4 plus x over 3, 2.3 to 2.4, giving me 0.1 over 3 plus 0.1 over 3 plus 0.1 over 3, which is equal to 0.1. So that's your final probability answer. Okay, so any questions on this problem?
Um,
Uh-huh.
so, uh, uniform random variables, um, was that, are they geometric in nature? Was that the reason for 1 over b minus a?
No, they are not geometric in nature. They are, in fact, they are not related to geometric random variable at all. So, yeah, so the CDF or the CDF has of the uniform random variable has a property that it is going to be a straight line between A to B, which means that the rate of change of this line is going to be the same everywhere, which is equal to 1 over b minus a.
Oh, yeah, okay, I remember now.
Yeah,
All right,
yeah,
thanks.
yeah. So are we good with this problem? If you agree, please unmute your microphones and say aye. If not,
Aye.
let me know.
Aye.
Okay, all right. And as a check, are Alexis, Cordero, and Monica also in?
Yes, Professor.
Okay.
I'm here, Professor.
Okay, very good. Monica?
Yes, for sure.
Oh, thank goodness. Okay, because I just saw your messages that you were not able to get in. Okay. Now, so those students that were a little bit late, so we are solving these instructional problems that are on Canvas. It's on file. It's a file named 127 27th March.pdf. So you can download that, or you can just look into my screen, and I'm going to show you the problems that we are working on. So that was the first problem that we worked on. So we are recording this proceedings. So whatever you have, whatever questions you have, you can always revisit here. Okay. Okay, so now let's solve problem number 2. So finally, there's a cure for zombie virus on Walking Dead. So after vaccination, the time it takes for the fever to come down is exponentially distributed with an average time equal to 10 minutes. What is the probability that the patient's fever comes down within 5 minutes? So this problem is actually telling you that it is exponentially distributed with average time equals to 10 minutes. And if you recall, for an exponential random variable f of x, the PDF takes this form: lambda times e to the negative lambda x for x greater than or equal to 0, and it is 0 otherwise. And the expected value, or the average, is 1 over lambda. In this case, x is the time for fever to come down. So construct the probability density function here and try to find this probability that the patient's fever comes down within 5 to 10 minutes.
Five to 10 or 0 to 5?
Within 5 minutes. I'm sorry if I said 5 to 10 minutes. It's yeah, you're right. From 0 to 5. You can also use Slack channel to share your answers with your peers. So if you were to go to 127 page, you can upload your snapshots. Whatever work that you're doing, you can also upload the snapshot of it. Okay, so do I have a probability value? Your probability value will be in terms of exponents.
I got 1 minus e to the negative 1/2.
1 minus e to the negative
E
1
to the negative
half.
1/2.
Okay, anyone else? Okay, so do we still need some time, or should I start solving this problem? If you are ready for me to solve this problem, please unmute your microphone and say aye.
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 Okay. All right. So let me solve this problem, and let's see if 1 minus e to the negative 1/2 is the correct answer or not. So the average time is equal to 10 minutes. So it tells you that the expected value of x, which is the time it takes for the fever to come down, is 10 minutes. An exponential random variable has this property that 1 over lambda is your expected time. So it implies that lambda is equal to 1 over 10. So if I were to plug 1 over 10 here, my PDF will be 1 over 10 times e to the negative x over 10 for x greater than or equal to 0 and 0 otherwise. I need to find the probability that the fever comes down within 5 minutes. So I need to find the probability that x is less than or equal to 5. So I need to find the integration from 0 to 5 of e to the negative x over 10 dx. And when I solve this integral and plug in the limits, when I plug in a 5, I get negative e to the negative 1/2. When I plug in a 0, I get a negative 1. Negative and negative give me a positive 1. So 1 minus e to the negative 1/2. So indeed, Mason is correct. So that's the probability, 1 minus e to the negative 1/2. Now, when we solve problems with continuous random variables, it's really very important for you to make sure that your limits are appropriate. So your exponential random variable in this case is modeling the time. So it has to be always greater than or equal to 0. Sometimes you may have or some students may have the tendency out to, putting the limits like this from -infinity to 5, which doesn't make sense. There's no such thing as negative time. So this has to be 0 to 5. Okay, so if you are good with this problem and if you have no questions, we can move on to part B. If you're ready, please unmute your microphones and say aye.
Aye.
Wait a minute.
You have a question, Seth? Okay, tell me.
Yeah. Okay, so at the very end of this problem, we end up getting negative e to the 1/2 minus -1, right? But then in the oh no, I didn't see the 1 there. Okay, never mind. I'm good.
Yeah, so this is the 1. Yeah. Okay. All right. Now let's solve this problem. A patient's fever has not come down for 15 minutes. What is the probability that it comes down within the next 5 minutes? So here you have some sort of an a priori information. So conditional probability will be at play here. So try to solve this problem. Try to have a chat with each other. Use Slack channel to take snapshots of your work and upload it on channel 127 to show your partial work to your peers. If you have any questions, please feel free to unmute your microphones and ask.
I'm guessing we're not supposed to get a negative number.
No, you can never get a negative value for probability, are you?
Yeah.
Okay, so make sure that you have set up your problem well. So X measures the time it takes for the fever to come down, right? And it is given to you a priori, or it's an a priori information that X is definitely greater than 15 because the fever hasn't come down for 15 minutes. And then the question goes on to ask you what's the probability that comes down within next 15 minutes. So isn't it kind of saying to find the probability that X is less than 20, given that X is greater than 15?
Oh, given. Okay.
Right? Because it's given to you that the fever hasn't come down for 15 minutes. So use this conditional probability formula. Probability of A given B is probability of A intersection B, or A and B, or probability of B. Okay. So do you guys have the integration set up? So Lewis is there. Okay. Okay, Mason. Yeah, go ahead.
Would it be the integral of from 15 to 20 of lambda e to the negative lambda x dx over the integral of 15 to infinity of the same thing.
15 to infinity of the same thing. That's perfect.
Okay.
That's perfect. Yep. This is what you need to find out. Is Lewis was Lewis able to join? Is Lewis here?
Yeah, I'm able to join.
Okay, very good. Thank you. Okay. So now I think it's a good time for me to discuss why this is the correct integration setup. So I need to apply the conditional probability because it is given to you a priori, or it's already given to you that the fever hasn't come down for 15 minutes. So that tells you that x is definitely greater than 15. And we need to find what is the probability that it comes down within next 5 minutes. So it's asking you what's the probability that, hey, even if this information is there, what's the probability that x is less than 20? So I need to use this conditional probability formula. Probability of A given the event B is equal to probability of A and B or probability of B. So this equation now boils down to probability that x is less than 20 and x is greater than 15, or probability that x is greater than 15. X is greater than 15 and x is less than 20 and x is greater than 15 essentially means between 15 to 20, right? Because these are all the points that are greater than 15 and these are all the points that are less than 20. So I'm looking at this interval right here from 15 to 20. So indeed, the integration limits will be from 15 to 20 times lambda times e to the negative lambda x dx, or next, probability that x is greater than 15. This term can also be written as probability that x is greater than 15 but less than infinity. So from 15 to infinity, lambda times e to the negative lambda x dx. So can anyone give me the value for this integral except for Mason?
I can figure out the numerator. I think it's it basically be e to the negative 2 minus e to the negative 1.5 for the top, right?
E to the negative 2, e to the negative 2. Can you repeat that again, Seth?
E to the negative 2 minus e to the negative 1.5.
I think you should get e to the negative 1.5 minus e to the negative 2.
Oh, okay.
Right? Yeah. And then the denominator will be e to the negative 1.5. Okay? So, and I can manipulate this equation. Yeah. Because when I integrate from 15 to infinity, lambda times e to the negative lambda x, here in this case, lambda is 1 over 10. So x over 10, the limits are from 15 to infinity. When I plug in an infinity, it goes to 0. When I plug in a 10, I get negative 1.5. So this negative and this negative becomes positive e to the negative 1.5. All right, that's how you get the denominator.
Wait, hang on. So in the previous problem, we did the e at the max interval minus e to the minimum interval, didn't we? It was e to the negative 1/2 minus negative 1.
No. Yeah. See, when you plug in 0, it gives you negative 1. So it's still upper interval minus the lower interval.
Yeah, I know. Down here, you're doing the.
When I plug in the upper interval, infinity, the e term becomes 0.
I know. I know. I'm talking about the numerator. You have the lower interval minus the upper interval.
So that's because
The chain rule from the negative when you integrate it from the exponent, it comes down.
Yep. So okay, let me solve the numerator here. Let's do the numerator part. Okay. So I get.
Oh, okay. I
there we go.
get it now.
Okay. All right. Okay. So the video is the proceedings are being recorded anyway, so you can always replay it. So from the numerator term, I'll take e to the negative 1.5 common as a common term. So I get 1 minus e to the negative 0.5 or e to the negative 1.5. So these two terms cancel out. So I get my final probability answer as 1 minus e to the negative 0.5. So that's the further simplification. Now, for the purposes of your exams, I would like to see a correct setup of an interval of integrals. That will give you about 90% of your points. The remaining 10% is getting the proper numerical answer. So you should strive to get your integral limits correct. Okay, so can we proceed further? All in favor?
Aye.
Okay.
I
Okay. Okay. All
Is there a
right.
What
chat?
happens
Is
to
there a chat
lambda?
window that we could just like put like +1 or -1 or something like that?
Yeah, you can do it on Slack channel if you want. Because when I share my WebEx, I'm unable to, for some reason, go back to the chat window. So if you have Slack open, you can do +1 and -1. You're talking about agreements to move forward, right? Are you there, Jerry?
I'm sorry, I was talking and I didn't hit unmute.
Okay.
Yeah,
Okay.
that's what I was talking about.
Okay. Yeah, you can say +1 or -1, or if I
But
move forward.
if it's more difficult to do that, then we can just stick with what we're doing.
Okay. Okay. Cool. All right. So let's solve problem number 3. The average time between two patients receiving the vaccine is 5 minutes and exponentially distributed. So let's say that there's a patient here, there's a patient here, and there's another patient here who is currently receiving the vaccine. The time between these two patients is exponentially distributed with an average value equal to 5 minutes. Rick Grimes, however, is the third patient in line. So he's the third success. So what's the probability that he gets vaccinated within the expected time? So here I would like for you guys to think the time that Rick Grimes has to wait, whether it be exponential or whether it be some other kind of random variable.
Well, this is based off, trial keeps going until the first success. So wouldn't it be binomial?
No, it's not going to be binomial. Binomial is discrete.
Oh, no, you're
Yeah,
right. You're right.
Remember, we are modeling the time until Rick gets vaccinated.
Oh, okay. So,
Or does it just matter that Rick Grimes gets it?
Here, in this case, you're given the time between two patients as 5 minutes, right? And that is exponentially distributed. But Rick Grimes is the third success.
Okay, so it'd be an
Yeah.
Erlang random variable.
Very
then.
good. Very good. It's going to be an Erlang random variable. So recall from one of the videos that Erlang random variable models the time elapsed until the third success. Exponential random variables happen to be a very specific case of Erlang where you're modeling the very first success. It's just like how geometric and Pascal are related to each other. Pascal discrete random variable models the number of trials until the nth success. Erlang random variable, it models the time until the nth success. And here you're modeling the time until Rick Grimes gets vaccinated. So use the PDF of an Erlang random variable here with n is equal to 3. So an Erlang random variable. So let's say that let y be the time, or you know what, just for brevity and for clarity, let's use x. Let x be the time until Rick gets vaccinated. X is Erlang because he's the third success. N is equal to 3, third success. So the PDF of an Erlang random variable takes this form: lambda to the n is 3 here, times x to the n minus 1. So 3 minus 1 gives you a 2, e to the negative lambda x over n minus 1 factorial, so 2 factorial, for x greater than or equal to 0. And for Erlang random variable, the expected time is n over lambda. So 1 over lambda is the time, is the average time between two customers, which is given to you as 5 minutes here. N is 3, so expected value of x in this case is 15 minutes. So Rick can expect to wait for 15 minutes until he gets vaccinated. But in this question, you're asked, what's the probability that he gets vaccinated within the expected time? So you need to find the probability that x is less than or equal to 15. So what I would like for you guys to do is just set up the integration and give me the limits.
What is the denominator?
2 factorial.
Okay.
Yeah, because the Erlang's form is something like this. I'm going to upload it on the Slack channel here. Okay, so let me ask Louis this question. So Louis, do you have your integration set up? You can talk to your... Almost? Okay. Whenever you have it, just let me know. Don't worry, guys, if you don't set it up correctly. It's totally okay. These sessions are meant to make mistakes and learn. So no pressure. Okay.
Are we still using the same problem?
Yeah, we are still talking about problem 3.
So it would be from 0 to 5?
From 0 to 15. Yeah, because we are interested in finding the probability that x is less than or equal to 15. Because the expected value, or the expected time that Rick has to wait is going to be 15 minutes. Because every customer on an average takes 15 minutes to get served. Rick happens to be the third customer. So it makes sense that he has to wait for 15 minutes as an expected time. And the question is, what's the probability that he gets vaccinated within the expected time? So the limits of the integration will be from 0 to 15, lambda cubed times x squared times e to the negative lambda x or 2 factorial. Now, this integral evaluation, how many of us are not comfortable with this form? Or how many of us think that, yeah, this is a little bit tricky and I need to solve, or I need to be shown how to solve this?
Yeah, I'd like you to go over if you don't mind.
Like to go over it? Okay. All right. So is everyone ready until this point?
Yeah.
Yeah?
Yes.
Okay. All right.
Yeah.
Okay. So okay. So let me erase this portion and set up the integral, because I would definitely need space for this problem. So I need to get integration of lambda cube times x squared times e to the negative lambda x over 2 factorial dx. I'll plug in the limits later, but let's solve this problem. Now, problems like this, where you have a function which is expressed as product of two functions, can be solved using a technique called integration by parts. Okay, so in integration by parts technique, what I do is I create two columns. This is column 1 and this is column 2. In column 1, I'm going to place a function which is easily differentiable, and that is x squared in this case. A function which is easily differentiable gives you a 0 upon repeated differentiation. So for example, if I were to repeatedly differentiate this guy, I get 2x next, then d by dx gives me 2, and another d by dx gives me a 0. So such a function is easily differentiable. So x squared happens to be the function 1. Then lambda cube e to the negative x will be the function which is easily integrable. An easily integrable function is one that does not grow, that doesn't blow up. Okay. For example, if I were to integrate x, I get x squared over 2. If I were to integrate this again, I get x cubed over 6. So you can see that, the exponent, the power of x, it just blows up if you were to repeatedly integrate it. So I'm going to place lambda cubed times e to the negative lambda x over to the second column, and I will integrate along the second column until I match the 0 of the first column. So when the first time when I integrate this function, I get negative lambda squared times e to the negative lambda x. Then when I integrate it one more time, I get lambda times e to the negative lambda x. When I integrate it one more time, I get negative e to the negative lambda x. Then after that, I'm going to join these terms using these diagonal lines and label them with positive and negative signs like this. All right. Next, what I'm going to do is I'm going to multiply the terms that appear at the ends of these arrows. Whatever product I get, I multiply them with either +1 or -1, whichever sign is appearing on these lines, and then I will add all of those products together to give my final integration answer. So in this case, I multiply x squared with this term here and multiply the resulting product with a +1. So I get negative x squared times lambda squared times e to the negative lambda x. When I multiply 2x with this guy, I get 2x times that guy. Then I need to multiply it with -1 and add it to the running sum. So I get 2x times lambda times e to the negative lambda x. And similarly here, I get -2 times e to the negative lambda x. Now my limits are from 0 to 15. They are from 0 to 15. So then I plug in 15. It's going to give me a quite messy answer, actually. 15 squared times lambda squared times e to the negative lambda 15 minus 2 times 15 times lambda times e to the negative lambda times 15 minus 2 times e to the negative lambda times 15. So that's what I get when I plug in a 15 minus when I plug in a 0, x squared, 0 squared gives me 0. So this first term disappears. Second term also disappears because of an x here when I plug in x as 0. But the third term, it gives me -2 times e to the negative 0, which is essentially 1. So it gives me -2. Negative and negative gives me a +2. So my answer is 2 minus 15 squared lambda squared e to the negative lambda 15 minus 30 times lambda times e to the negative 15 lambda minus 2 times e to the negative 15 lambda. And then I forgot this 2 factorial in the denominator. So over 2. So that's the probability. And you can find the numerical answer by plugging in lambda as 1/5. So that's how you solve problems using integration by parts. So use this graphical method and you'll find that most of the integral problems that look seemingly difficult will actually be quite simplified. So let me know if you have any question on this one.
Professor, I actually remember you going over this in one of the videos. Say, for instance, if it were 0 to infinity instead of 0 to 15, all of all of the terms where it's like e to the negative lambda 15, all those
That's
would
it.
actually go to 0. All those
Yep.
would actually go to 0. Okay, because e to the infinity or negative infinity, whichever makes the whole term go to 0.
Yep. Yep.
Okay, cool.
Okay. All right. So we have one more problem remaining, and that is there are two kinds of vaccines, vaccines A and B. The patient is twice as likely to be administered with vaccine A versus vaccine B. When the vaccine A is administered, the time it takes for the fever to come down is exponentially distributed, with average time equal to 5 minutes. And when B is administered, the time it takes for the fever to come down is 10 minutes. Rick's fever came down in 3 minutes. What's the probability that he was administered vaccine B? So my hint to you guys is think about tree diagrams, because there are two sequential experiments. A particular kind of vaccine is chosen with certain probability, and then there's a certain probability with which the fever comes down after a given time. If you have any questions, please unmute your microphone and let me know. Okay. So most likely you'll have to draw a tree diagram. So does anyone have a tree diagram? If so, just take a snap of it and upload it on Slack so that I can see it. So does anyone want to discuss or share their thought process? Okay, so do you guys want me to work on this problem now? Please let me know. You can say aye.
Yeah,
Yes, please.
Okay. All right. So I'll try to solve this. I'll give you a partial solution to this problem, and the remaining part I would like for you guys to do it on your own. And after some time, I'll upload this PDF anyway with the complete solution. So let me give you the partial solution because we are almost running out of time. So there are this experiment is actually comprised of two sub-experiments. One is you select a vaccine type, and then you measure time for the fever to get down, or fever to go down. So this can be solved using a tree diagram like this. So you have a root, so you select a vaccine type, either it can be A or it can be B. And it's given to you that vaccine A is twice as likely to be administered versus vaccine B. So what's the probability that Rick was given vaccine A? If I were to choose, or rather, if I were to choose a vaccine, what is the probability that I choose vaccine A?
2/3.
2/3. So the probability of vaccine B is 1/3. So let's say that this vaccine was chosen. So the probability that the fever comes down within 3 minutes needs to be evaluated using the exponential distribution. So here it will be an integration from 0 to 3. The lambda, the average time for vaccine A is 5 minutes. It's given to you that it's 5 minutes. So lambda is 1/5 for vaccine A. So here I will have this integration set up. So that gives you the probability of fever coming down within 3 minutes given that vaccine A was chosen. So this is the probability of this branch here. Probability of this branch will be probability that X is less than 3 given vaccine B. So I need to use the PDF for vaccine B. So the average time it takes for vaccine B to kick in is 10 minutes. So here the integration will be from 0 to 3, 1/10, e to the negative x/10 dx. So these leaves right here tell you some information. For example, this leaf, this leaf here, it is telling you vaccine A and fever coming down in 3 minutes. This one is telling you vaccine B and fever coming down in 3 minutes. But the question is, what's the probability? What's the probability that he was administered vaccine B, given that his fever came down in 3 minutes? So we need to find the probability of B, given that X is less than 3. So I can use conditional probability here. Probability of vaccine B and X is less than 3, or probability of X is less than 3. So the numerator term can be obtained by tracing the path in this tree diagram from this root all the way to this leaf here. So that gives you 1/3 times integral from 0 to 3, 1/10, e to the negative x/10 dx. Now the denominator term, both of these leaves include this information that X is less than 3. So probability that X is less than 3 can be obtained using vaccine A, and you get time less than 3, or you administer vaccine B and time is less than 3. And therefore, you can get these probability values by tracing the path from the root all the way to these leaves. So probability of vaccine A and X is less than 3 is 2/3 times this integral here. So that gives you something like this. So that's a numerator term. The denominator term is 2/3 times 0 to 3 integral of 1/5 e to the negative x/5 dx, plus probability that vaccine B and X is less than 3 is 1/3 times 0 to 3, 1/10 e to the negative x/10 dx. So when you solve this integral, you get your final answer. So that's how this problem is solved. So I'll post this PDF on Canvas, and you can also record, or you can also go over the video recording or the recording for this proceedings, and you can try to understand how this problem is solved. If you have more questions, then we can have a chat over the Slack channel. So does that sound good to everyone?
Yep, sounds good.
Sounds good.
Yep.
Okay.
Are we able to get access to these PDFs to print them before we start?
I will. Yes. Next time I'll give you an access quickly. So yeah, I'll do that.
Awesome.
This recording will be posted, right?
This recording will be posted on. I'll try to post it on YouTube if possible. Will that work for everyone?
Yeah.
Yep.
Yeah.
That works.
Okay. Okay. Now, before I let you guys go, let me ask you this question. So, are you guys having any challenges to get on WebEx? Because I noticed that Alexis, Cordero, and Monica, and some others, they had some initial problem to get on WebEx. So, can you let me know what the problem was?
For me, the problem that I had was I'm only able to join meetings if I go directly to the emails that you send out and click join meeting there. I can't open the app from my desktop or in my Windows Explorer, or else it just crashes right away.
Okay.
So the solution to my problem was just go to the email that you sent and click join meeting directly, and it'll open up a browser thing, and then you open up WebEx after that.
Okay, so can we agree that for ECP 127, I'll send out emails with the links and you'll click join there? Will that work for everyone?
That's what I did today. I think that works.
Could you also post links to the lectures on the Canvas somewhere? Sometimes they're not working when inbox, for me at least.
Links to what? The lecture videos?
The lecturettes, yeah.
Oh, they should be on Canvas announcements. So are you not able to see the
Oh,
announcements?
okay. I guess I just didn't see them in the announcements.
Yeah, so when you, let me just show this one more time. So are you guys able? Okay, I'll start broadcasting. I promise I'll let you guys go in a bit. So when you go to Canvas here in announcements, when you go to announcements, here you have class agenda for week of March 23rd. So I'll name all of these announcements like this: class agenda for the week of whatever. So you will go there and you'll just click these links and it will open up a nice YouTube video for you. And you can solve and you can go over it.
Perfect.
All right. Mm-hmm.
Thank you.
Okay. And anything else? Any other questions?
Nope.
Okay. All right. So I hope this session was useful. I'll keep posting these videos and let me know. Please give me your feedback on these videos because this is the first time that I'm trying to make these videos and trying to create my own YouTube channel here. So give me a like or two or thumbs down if you think that video. Next time in my videos, I'll like, please subscribe and the subscribe button.
Oh no. Okay.
Self plug.
Let's make Professor go viral, everybody.
Yeah.